So in this time I'm going to be proving that you can diagonalize any matrix using its eigenvalues, the Peyam's way. So you have A, and I claim that it's going to be equal to the set of the matrix created from the V eigenvectors, the corresponding eigenvalues on the diagonal, and then the inverse of the matrix created by the eigenvectors. Now, how do I know this? Well, let's move it down here. So here I'm going to have our matrix V1, 1, V1, 2, dot, 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 all the way down until V1, N. And we're going to go crossed and diagonal, not like that. And until we get to VN1, all the way down until VNN. Okay, and we're going to multiply this by the eigenvalues. Alright, sorry for the poor handwriting. I'm not used to writing like this. And we have the other one, the inverse of it. Get rid of that equal. Okay. So now, what is this going to be equal to? Well, it's going to be this one times this one, right, in the first column. So we're going to have lambda 1, V1, 1. Okay, now let's go down a row in the multiplication, right? Then we'll get lambda 1, V1, 2. Lambda 1, V1, 2. Carry that on down until you end up getting lambda 1, V1n. All the other ones would be 0, right? Because you're going across here, down there, but all the way down from lambda 1 is all 0, so all of these other will be canceled out. Okay, now let's focus on the next row, which is not seen, but you can imagine it. It'd be lambda 2 times all of the components of your second eigenvector, and then same all the way down until you'll get Vn1 because you're going across here, and then you're multiplying it by zeros except for lambda n. So we'll get times lambda n all the way down until lambda n times Vn n, right? So there we go. But what do we know about lambda, the eigenvalue times the eigenvector? It's just the matrix A times each individual one. That's what this is showing. And maybe I'll prove it in another video, but this is the same thing as A times your V1 Vn. Okay? Right there. Okay. So now what we can substitute that in for here. Right? So then we get that we have A times all of these things, right? Because we substituted it in, times the matrix of all those things inverse. And of course we get A times the identity, which is just A. So I'm actually going to prove that A times each individual vector in here, the thing generated by that, is the same as just A times each individual one. So that'll complete the proof that you can diagonalize using the eigenvalues. So here we have the multiplication, and I'm going to prove via the multiplication that this is just applying A to each individual vector. So we're going to go across here, down here, right? So we're going to get the sum of AI1 and then B1I. Okay, so that's going to be up here. And then the second one is going to be here and still down. So it's going to be the sum AI2 V1I. Continue that down. Sum AI N V1I. And you can do that for the rest. Right? It continually is true. I'm not going to show it, but makes sense, right? And it turns out that this right here is equivalent to just doing that. Okay? So that right there is the same as that, and you can see obviously that it is true. So it's an obvious fact that A times V1 to Vn is going to be A B1 to A Vn. And that'll conclude our proof. Our QED. That's not good.